Example 6.2. A wire is tapered such that it connects two straight sections. Section 1 has a diameter of 4R, while section 2 has a diameter of 2R. The wire is copper and carries a current. Assume that the current is uniformly distributed across any cross-sectional area through the wire's width. In the second section, there is a voltage drop of 10 microvolts over a 2-meter length. Draw an accurate sketch of the situation, and then finally, what is the drift speed of the electrons in section 1? First, we got to sketch this complicated description. So let's sketch this complicated description. So we know that a wire is tapered from a wider to a thinner section. So I imagine that I have a thick section. Let's say it's looking about like this, and then it tapers off to half the thing here. So I'm going something like that. So here's my wire. And then I want to put into the details into this picture. So I know that the wider region has a diameter of 4R, and I know that this has a diameter of 2R. And so this sets up section 1, and this sets up section 2. Now, because current has to be constant, we know that according to the volume flow rate, right? Maybe I should write that down. From AV equal to a constant, that means if I look at a drift charge right here, this guy's going to have a drift velocity, which I'm going to call V1. So what this is telling me here is that the area of 1 is big. That causes this drift speed to be smaller. So when I get to right here, that drift speed has to be larger. So then that guy has to be larger in order to keep this guy equal to a constant. So we know the drift speeds have to change. So then they're telling us that there's a voltage drop across a 2-meter length. So let's set that up. So let's say that from here to here, this is my length, which is 2 meters. And then I'm going to have a voltage drop from here to here, which I'm going to call delta V2. And they say it's 10 microvolts. So that's where I get, that's my picture right there. Now, another thing is that we're dealing with copper. So we're going to need to Google some constants here. Okay. So since this is a copper wire, we need to Google two constants associated with the microscopic Ohm's law. One, it has to be the concentration of copper. So when I Googled it, I got 8.49 times 10 to the 28, per meter cubed. And the other one is that Ohm's law requires the resistivity. So then I looked at the resistivity of copper, and I ended up finding 1.69 times 10 to the minus 8 ohms meter. Now, if your numbers slightly vary from this, I wouldn't worry about it, right? Because that's what you Googled. So now that we have this, now we could go in and start looking at the physics in part B. First of all, as we've already said, the current from section 1 to section 2 does not change. But the current densities do. So I know that the current must remain the same in each of these. But then that tells us that we can also write the current or the current density as the current divided by the area, which then gives us this relationship that says that the current density in area 1 times the current density in area 2, this also has to remain a constant. But we know the areas. So if I go ahead and solve for J1, because that's what we're really looking for, we're going to have that J1, the area of 1 is then going to be pi, but these are diameters, so I have to divide by 2 of 4r squared. That's going to be J times pi of 1/2 2r squared. And so when the dust settles, we see that the current density in the section has to be 1/4 of the current density in 2. Now note that this makes physical sense. And the reason why that makes physical sense here is that that also tells us here that the drift velocity in 2 must be greater than the drift velocity in 1. That's what that current density is telling us. So far that looks good. Now we need to focus on calculating J1 and J2. So now our focus is in calculating J1 and J2. So to calculate J1, we need to rewrite this in terms of the drift speed. Which is, of course, V1. So if I do that, what we saw here is that the current density is then equal to the concentration of copper times the charge times the drift density 1. So right away, we have our first current density. Now, on the other hand, we have to worry about the current density at 2. So what we'll look at here is that the current density, J2, deals with section 2, which means here is that, so we need to look at those details. So when I look at this, I have my wire. Okay, so here's my wire, and this is fixed in length. And I could calculate the drift velocity. We don't need to, though. And the reason why we don't need to is that, yes, I have a drift velocity right here. And I know that this guy has a drift velocity of v2. And we could do the algebra to do that, but there's an easier way to do this because we're given the length. And the length here is 2 meters. And we're also given the voltage across section 2, which is 10 microvolts from here to here. So that means here I have the ability to calculate the electric field in this situation. So as a consequence, we could use Ohm's law to calculate this thing. So Ohm's law says what? So if I look at Ohm's law, in microscopic form, of course, we see that the current density has to be the electric field divided by the resistivity of copper. So the only thing we got to do here is we got to calculate that electric field. But we know how to calculate the electric field because it's the slope of the potential, which then that means I have this guy, there's my slope, divided by the resistivity of copper. So now here is J2. Now we could put all these 3 boxes together. I could substitute J1 into J1 equals to 1/4 times J2, and I could substitute J2 into that top equation right there. So let's go do that. So now I'm going to substitute everything into the J1 equals to 1/4 J2 equation. So if I do that, we then say that we have J1 equals to 1/4 of J2, which then says that I can replace J1 with N of copper times the charge of the electron times the drift speed right here. And then on the right-hand side, I'm going to get 1/4, and then I'm going to get the resistivity of copper times the length divided into the voltage V2. So isolating V1, we get that V1 is then going to be this. It's going to be 4Le N of copper times rho of copper divided into the voltage V2. So if I start putting in my numbers, I'm going to get 4 times 2 meters. Then I need the charge, which will be 1.60 times 10 to the negative 19 coulombs. Then I have my number density, which is 8.49 times 10 to the 28 meters cubed. And then finally, I have my resistivity, which is 1.69 times 10 to the minus 28 ohms meter. And all of this is going to go into the voltage, which is 10 times 10 to the minus 6 volts. So that's a lot of numbers. So what you should do here is to try to make things nice for you. Look at all the powers of 10. Try to isolate the powers of 10. So if you look at the powers of 10s, what I would do, because you're still going to have to put this into a calculator or an online calculator, and the first thing I'm going to do is that I'm going to just pull out the numbers. So I'm going to get, let me bring it down here a little bit further. So then I'm going to pull all the numbers out. So I'm going to get 4 times 2 times 1.60 times 8.49 times 1.69. But then I'm going to look at all of the powers. So look at that. That's minus 19 plus 28. Oh, that's a mistake right there. That should not be. Okay, I wrote negative 28. That should be negative 8. And so then this is minus 8. So if I look at this, then this is 10 times 10 to the 6, negative 6. So this is really 10 to the minus 5. So now if you look at this, this is minus 27 plus 28. Note that that's just times 1. Times 1. So I don't have to do all that fancy putting into the calculator thing. So now I've reduced all of my powers to a factor of 10 to the negative 6. So then this means here I'm going to get all of these numbers, and this will be 10 to the minus 5 over 10, which of course is then 10 to the negative 6. But if you put everything into the calculator, I get 5.44 times 10 to the minus 9 meters per second. So if I look at this, I now have my drift speed.